At 200 kilometers per hour, this looks like a collision with a solid surface. But that familiar phrase, water becomes concrete, is wrong. The water has not changed phase. It is still a liquid. The real danger is how much momentum must be transferred to that liquid, and how little time the body may have to slow down. 200 kilometers per hour is 55.6 meters per second. For an illustrative 75 kilogram body, that speed represents about 116 kilojoules of kinetic energy. That number alone cannot predict an injury or a G-load. It tells us only how much motion must be redirected or dissipated. The outcome depends on how the impact unfolds: orientation, exposed area, stopping distance, water conditions, and the structure of the body all matter. The key idea is deceleration. Acceleration is the change in velocity divided by the time over which that change occurs. If the same change in speed happens over a shorter time, the magnitude of the deceleration is greater. A seat belt, an airbag, and a crumple zone do not make a car's kinetic energy disappear. They extend the stopping process and control how the load reaches the occupant. Water impact is another version of that problem, but the stopping medium moves and deforms around the impacting body. The physics is hydrodynamic, not magical. Water impact models include a term that grows with velocity squared and another connected to the effective, or added, mass of water accelerated around the object. At low speed, water has time to flow away. At high speed, a large volume must be accelerated in a fraction of a second. The resulting pressure and force can rise rapidly even though the water remains liquid. Geometry changes that interaction. A broad, flat surface meets more water at once. A narrow shape introduces less area first and can extend the entry over a longer distance. This is why a belly flop hurts at a swimming pool and why engineers study hull angles, capsule attitudes, and impact velocity during water landings. The comparison explains the mechanism. It does not make any high-speed human entry safe. One of the most cited human datasets is a 1965 Federal Aviation Administration report. It examined 44 known survivors of high-velocity falls into water. In that historical analysis, feet-first entry was reported as 5 to 7 times more survivable than other orientations. The proposed reason was a longer deceleration time produced by a smaller initial braking area. But this was a survivor case series, not a controlled experiment, and the report did not define a universally safe height or speed. The injuries were still serious. In the FAA cases, feet and buttocks first impacts frequently produced fractures and characteristic contusions. Other orientations were associated with extensive internal trauma. A position that performed better within one historical dataset is not the same thing as a safe technique. A 1981 Journal of Trauma study reviewed 100 consecutive autopsies after jumps from the Golden Gate Bridge and compared them with 6 survivors. The fatal cases appeared to enter horizontally and experience maximal deceleration, while 6 survivors entered feet first with more gradual deceleration. Many of those survivors still suffered major injuries to the lungs, liver, or spleen. Again, orientation changed the load, it did not eliminate it. Spacecraft engineers work with the same basic problem under tightly controlled conditions. NASA treats splashdown as an engineering problem, using simulations, instrumented mannequins, and drop tests to measure acceleration and reduce injury risk. Capsule attitude, vertical and horizontal velocity, seat design, restraints, and the duration of the acceleration pulse are all considered together. A successful splashdown is engineered long before the capsule reaches the ocean. So why can water hit so hard? Not because it becomes concrete. It is because speed gives the moving body substantial kinetic energy. Water must be displaced rapidly, and the resulting change in velocity can happen over a very short time. The surface is not a wall, but at high speed the body may not have enough distance or time to benefit from that difference. That correction is more interesting than the myth. Water remains liquid. The danger comes from fluid dynamics, geometry, and the unforgiving mathematics of stopping too fast.